the mass number of things. Alright? We can see on the periodic table, if you look at any of them, that they've got two numbers. There's one whole number on any of them. Can somebody tell me what that whole number is? Or what it represents?
The atomic thing.
The atomic number, that's good. Somebody tells me what that tells us about it. We have the atomic number, it tells us the number of protons. Great job, Nate. Thanks. So that leaves us with the other number, which is usually has a decimal. It's like way more specific and a much bigger number. So let's write that down. We have our atomic number, and you told us that's the number of protons. Then we have our atomic mass. I'll write that in different colors. So this is the other number here. It's called the atomic mass. I already showed you guys the formula of how to calculate this once before. Do you remember what that was? What is it, Jenna?
Protons plus neutrons.
Good. So our atomic mass is our protons plus our neutrons. And we get the decimal point because it's an average based on different isotopes, which we're going to learn about and talk about today. So this is the first main part of what we need to do. We know that atomic mass is equal to protons plus neutrons. I'm writing that separate like a little formula because you're going to use it like a math formula today once we get into our work. Alright? These different forms of elements based on having different number of neutrons and different mass number is called isotopes. So an isotope shows us we can have different forms of something. Here we go. All right, carbon 12. That's the normal form of carbon. If we look at carbon right here, we can see, okay, carbon and its atomic mass is 12, 0.0108. So that means almost all of carbon is going to have a mass of 12. But sometimes, very rarely, it's going to have something more than 12. That's what increases that average just above the number 12. So we can have things like carbon 14. That's a naturally occurring isotope, it's a form of carbon that we might see. So using our atomic mass formula, let's figure out the difference between carbon 12 and carbon 14. So our mass of carbon 12 is 12, and it has how many protons? Anybody?
6.
6, that's right. And let's figure out how many neutrons it has. So we have to solve for n. I'm going to subtract 6 from both sides. This will tell me that 6 is equal to our number of neutrons in carbon 12. Now let's compare that to carbon 14. Our new mass is written right here, 14, equals, we still have the same number of protons, it's still carbon, it's still 6. Let's figure out our new number of neutrons. Subtract 6 from both sides. We're going to get what? 14 minus 6. 8. Good job. Okay, this number of neutrons, okay, who cares? It's still carbon, it still has a different number of neutrons. Why does it matter? It matters because this form of carbon, carbon 12, is at a stable and natural state. Whenever it has that many neutrons in the nucleus, it's called unstable, and that's known as radioactive. It can produce a beta molecule, which I don't know if you guys learned about that your freshman year or not. Is there an issue with it?
You're out of focus. You weren't on this. You weren't.
Oh,
You weren't.
that's
being-
okay,
You weren't.
that's okay,
Okay.
thank you. Yeah, so whenever it's radioactive, it can produce a thing that weighs 2 neutrons, basically, and it changes the weight of the whole thing. All right, the final step that we're going to deal with today is isotopes. So I saw this. So just like I said isotopes, ions. So just like isotopes is an atom with the same amount of mass, or a different amount of mass, ions have a different number of charges. So let's use lithium. I'm going to draw a lithium atom for us real quick. It's got 3 protons, usually 4 neutrons, unless it's an isotope of it. And then it's going to have 3 electrons. Okay? That's basically our idea. We've always, up to this point, matched our positive and our negative charges. What we're going to find out is that these atoms hate to have a weird number in their outer shell. Okay? This outer shell can hold up to 8 electrons, just like this first shell can hold 2 electrons. They like to have a full shell, they're happy with that. So right now, is this lithium happy? It's not happy. Would it be easier for this lithium, do you think, to gain 7 electrons to fill up the shell, or to lose 1 electron? Losing 1 sounds a lot easier than gaining 7. So that's what lithium and everything in this row tends to do. We're going to find some other element that's willing to take this electron from them. And they're going to send this electron over. So let's draw fluorine. It's got 19 total mass, so I'll 10 of those. And then it's got normally 9 positives. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first layer has 2 like it's supposed to. The outer layer has 7. It can hold up to 8. So both right here and right here, we have a empty spot, so to speak, as they pair up. This one, does it have a full shell yet? Not quite. Is it going to be easier to lose 7 or to gain 1? Gain 1. Look here, this one just says, okay, here you go. You take this one, gain this negative charge. It's just going to shed this whole outer layer. No more outer layer. Does this have a full outer layer?
Yep.
Does this have a full outer layer? They're both very happy now. They're both totally content. But this changes one thing about it. The charge. How many positive charges do we have here? How many negative charges? 4. Negative charges.
2.
2. So if we have 3 positive and 2 negative, that's going to leave me with positive 1. What about this one? How many negative charges does it have? 8 and 2, so it has 10. And how many positive charges? 9. So a total of negative 1. These are called ions. Whenever they've gained or lost a charge, what do magnets do whenever their opposite ends? What? Can you add 2 positives of a magnet together?
They
They don't stick. Right? The plus and the minuses stick together. So just like in a magnet, the literal same exact principle, these stick together because of that. Okay. I'm going to set up stations around the room. I'm going to put station 1 at your guys' table, and you two can start station 1. I'll put station 2 at your table. Devin, you can join him and start on station 2, station 3 at your guys' table, and you can start at your own stations. And after, let's say, 5 minutes, we'll switch to the next station. So come on over here, Devin. And everybody got one of the station papers, right? Okay, cool. Alright.
Isotopes represent the same element in various forms, specifically elements with a different mass because of a changed number of neutrons. Identify the difference between hydrogen 1 and hydrogen 2.
Nice, thanks, Gabe. So, alright, so you guys are looking at hydrogen 1, hydrogen 2. Whenever you see that name with the number next to it, that's telling you the mass that you're dealing with, okay?
Okay.
So instead of looking at the periodic table to try and find the atomic mass, because if you look at hydrogen, it's going to say 1.007. So that means most of them are 1, but every now and again, you're going to have a 2. So try and talk it out with each other, see if you can find a difference there. Did you guys read through it?
Yeah.
Cool. All right. Let me put this here where we can see what we're talking about. Good. All right. So number 1 says an isotope of carbon has 8 neutrons. What is its mass number? Think you could... Oh, wait. You already did figure it out.
Yep.
Good job, Jenna. Good job. Didn't put your name on your paper yet? What about you guys? Getting it figured out yet? Can I read through it with you? Cool. All right. I'm going to put my phone where we can see it. Ions represent elements with a varying amount of electrons. Since electrons don't have a mass, we can't identify a change in the atomic mass. Instead, we must base it on the electric charge. If an element gives up an electron, the negative charge, it will become positive. If an element gains an electron, the negative charge, it will become negative. That sort of makes sense, right? Just got to remember that the electrons are negative charges, so everything's sort of backwards. All right, so number 1 says sodium gives up an electron to chlorine when table salt is formed. What is the charge now of sodium, and what is the charge of chlorine? So let's remember, what is it giving up? An electron, a negative charge. So if it gives up, sodium gives up an electron, it's getting rid of one of its negative charges, right? So sodium will now become positive 1. And chlorine, that gains that electron, will now become negative 1. Does that sort of halfway make some sense?
Yeah.
All right. Write that down. Give it a try, guys. I'll come back around and see where you're at, all right? How's it going over here? You guys doing good?
Yeah, we got the answer, actually.
Okay, you said bigger mass. That's right.
Mm-hmm.
What part makes it have a bigger mass? Proton, neutron, or electron?
Neutron.
Neutron, that's right. So the only difference is hydrogen 1, well, it's made of 1 proton and 1 electron, and that's it. There's no neutrons. Hydrogen 2 is made of a proton and a neutron. So just say it has a neutron as well. You're writing on the wrong paper. It's all right. You can see when I first made that, I thought that maybe I'd give 1 to each of you guys, and then I decided just to make a answer sheet. So, yeah, I shouldn't have left all that space to write. What about over here? How are you guys doing by now? You finished your station?
Yep.
Good. That looks right, too. Good work. Here, let me show your work. Nice. Good job. Just wait a minute until the other stations are done. We'll move, okay? Nice job, guys. Good work. Nice. It looks like you got all the answers there. Can I show your answers real quick? Sorry.
Typically has
Nice. Good job.
the rate of 4 neutrons, right? So it would be stable or not?
All right, guys. Let's get ready to switch to our next station and keep moving on.